All right, good morning. With the snow day yesterday and changing up the plans with the ACT and the ACT work keys and all the things that happened yesterday and today that were supposed to happen, I've been asked this morning to go proctor the ACT work keys. So that's why I'm not in here. You have a sub in here right now. I will be back in towards the end of the hour once that ACT work keys is over. So I'll be able to answer a couple questions at the end of the hour. Hopefully I'll be in here by the end of the hour. So we're going to do a video again with this creating and actually doing the calculations with confidence intervals. So go ahead and get out your notes packet. And if you recall yesterday, or Tuesday that is, we were working with the critical values Z for proportions and T for means. For Z, we do inverse norm. For T, we do inverse T. Remember with T, anytime we work with a T distribution, we have to give degrees of freedom. And yesterday, right at the end of the hour, I had asked you to do these 4 examples. Hopefully you had a chance to do them. If not, I'm just going to show you real quickly the values and the calculations for this so that you have them in your notes, and then we're going to move on. So if we're doing a 96% confidence interval for a mean, this is going to be a T distribution. So T star is equal to inverse T. And my area to the left, that's the first command input that goes in here, my area to the left for this is going to be 1.96 divided by 2. And my degrees of freedom with 22 observations is going to be 21. So you go to your calculator, inverse T, which is in the distribution menu. Again, if you have a TI-83 calculator, you don't have this function. You'll have to borrow somebody's for the test. I'll have one that you can borrow. We're going to do 1.96 divided by 2, and my degrees of freedom is 21. Letting the calculator do that work, we get a critical value for T star of 2.19. Okay, moving on to letter B. Again, still a 96, but this time we're talking about it for a proportion. So this one is going to be a Z star value. We're going to be doing inverse norm. My area to the left is still going to be 1.96 divided by 2. My mean for Z's is 0, and my standard deviation is 1. So again, going to that distribution menu, inverse norm, 1.96 divided by 2, 0, and 1 gives me a Z star critical value of 2.05. One thing I forgot to do that is required for you guys to do is to label these. So this is the area, and this is degrees of freedom. Down here, this is the area, this is the mean, and that's the standard deviation. Notice that a T distribution up here has just a little bit more area included in the 96% confidence interval than a Z distribution does down here. Even though they're the same confidence level, the T star critical value is a little bit higher. Again, reviewing what we talked about the other day, the reason for that is because the T distribution is based off of a estimated standard deviation, whereas a Z distribution is based off of a known standard deviation. So because it is estimated, we give ourselves just a little bit more room for error than a Z distribution does. So we make our interval just a little bit wider. Okay, jumping down here to letter C. This is an 80% constant interval for proportion. Again, because this is a proportion, this is going to be Z star. So this is going to be inverse norm. My area to the left, 1.80 divided by 2. Mean of 0, standard deviation of 1. So this is my area. This is my mean. This is my standard deviation. Distribution menu, inverse norm, 1.8, 0, and 1 gives me a Z star critical value. Type something in wrong, sorry. 1.8 divided by 2, 0, 1 gives me a Z star critical value of 1.28. And finally, letter B, which should be letter D. We're doing a 99% confidence interval. Again, this is for means, so we're doing a T star, which is inverse T. My area is 1.99 divided by 2, and my degrees of freedom for this one is going to be 70. So inverse T, 1.99 divided by 2, degrees of freedom of 70, gives me a T star critical value of 2.65. Again, this is my area, and this is my degrees of freedom. So quickly recap from yesterday, or from Tuesday, finding our critical values. Now, moving on to the new stuff. In order for us to actually do this particular test, is what we're going to call it, to do this calculation, there are certain conditions that have to be met. And these are the same conditions that we talked about in chapter 7. We didn't call them conditions, but we're calling them conditions now because that's kind of the language that we use for these tests. So these are the conditions that allow us to go ahead and do a test or to do these calculations. And so we have to make sure these conditions are met for a proportion, and we have to make sure these conditions are met for a mean if we're going to be doing a confidence interval for proportion or a confidence interval for means. Now, when we get ready to go down the road, we're going to call this test a one proportion. Oops. Where's my... Let's start over. I don't know my ratio. This is called a one proportion Z interval. I'm abbreviating all of that. So a one prop Z interval. And this one is going to be called a T interval. Because once again, for means, we use a T star critical value. So we call this a T interval. The conditions, as we talked about in chapter 7, sample must be taken randomly. The 10% condition still must be satisfied. My sample must be less than 10% of my population. And again, what this 10% condition does is this validates the standard deviation. And finally, large counts. We have to make sure that it's a normal distribution. We're checking to see if it's a normal distribution. The large counts condition for a proportion, again, was that NP has to be greater than or equal to 10. N times 1 minus P has to be greater than or equal to 10. Now, once again, with this large counts condition, just kind of like we talked about the other day with Z and with T, we don't know the population proportion. That's what we're trying to estimate. We're trying to estimate this value, so we don't know this value. So what do you think we're going to use as an estimate for the population proportion? Just like we talked about on Tuesday, instead of using the population proportion, we're going to use the sample proportion as an estimate of the population proportion when we don't know it. Okay, so we're using P hat here to check our normal condition because we don't know the population proportion. Switching over here to means, when we talk about means for a T interval, it still must be taken from a random sample. My 10% condition must be satisfied. My sample must be less than 10% of my population. Again, this validates the standard deviation. And for my normal large enough sample over here, we're checking again to see if it is normal enough. This is that hierarchy. Level 1 was if the population is normal. Then we're good. Level 2 was the central limit theorem. If the population was not normal, but my sample size was at least 30, then we would say it was still normal enough. And level 3 of this hierarchy, this is new. This is where I told you guys we were coming with this. The population is not normal and we don't have a sample of at least 30. We have to graph your sample data. And what we're looking for is, are there any outliers? Or is there any strong skewness? And again, I'm going to emphasize the word strong. When we graph the sample data, it has to be really, really, really strong skewness in order for us to stop. Because we're using t, we're already giving ourselves a little bit more room for error. And so even if our sample isn't perfectly normal, as long as it is not really, really blatantly obviously skew, the t part of this still gives us enough of a margin of error there to allow us to continue. So that's why when we look at this sample data, we're looking for any strong skewness. So if any outliers show up or if any strong skewness shows up, we say it's not normal, we can't continue. But if there's no outliers, there's no strong skewness, we can go ahead and continue with the process. So those are our conditions for us to be able to actually do these calculations. We have to make sure the conditions are met before we do our calculations. So as long as we have those conditions that have been met, then we can go ahead and do our calculations. Let's practice real quick with these conditions and check to make sure they're met. First example here, we're doing a survey. That's the first 100 students to arrive at school one morning whether or not they slept at least 8 hours the night before. Only 17 students said yes. So first of all, you have to ask yourself, is this a proportions problem or is this a means problem? Yeah, you're going to have to think a little bit with that. So in this case, we're trying to find the proportion that say yes out of 100. So this is a proportions problem. Now we know which set of conditions we need to check. Most of the conditions are the same, but you still have to know that normal large counts condition is the one that is different. So you have to know whether it's a proportion problem or a means problem from the start. Also, it changes whether or not we use a z distribution or a t distribution. In this case, because this is a proportions problem, we're going to be using the 10 successes and 10 failures for our normal. And we're also going to be using a z distribution if and when we actually get to do the calculations. So the three conditions for proportions. Condition number 1, is the sample taken randomly? In this case, they stand at a door and they ask the first 100 students. Well, that's not very random. There could be some very obvious bias with that. Those first 100 students went to bed early, so they're more likely to have got more than 8 hours sleep, or those first 100 students were up early because they had to study or get there for some sort of thing, and so they didn't get 8 hours of sleep. So there is an obvious bias there with the first 100 people that they see. And so this is not taken randomly, so we cannot do this problem. Once any of the conditions fails, we're done. We stop, we move on. Okay, let's look at letter B. The following data amounts for vitamin C measures in milligrams per 100 grams blend for a random sample of size 8. Can we construct a confidence interval for the mean amount of vitamin C? So this is for a means problem. Okay, going up there and looking at the conditions, we know that condition 1 is random. And this does say this was taken from a random sample. For now, we're going to accept them at their word. If they said they did a random sample, yeah, we're going to believe that it's done randomly. When you are doing this in the real world, if you ever have a job where you're doing any sort of statistical work, you're asked to interpret statistics, you're going to spend a lot of time looking at that idea. Was that sample really done randomly? But for now, if it says random sample, we're going to accept them at their word and move on. Condition 2 is the 10% condition. So this sample of 8, is that less than 10% of all vitamin C? And there are hopefully more than 80 vitamin C pills. Okay, and finally, condition number 3. Because this is means, this is our hierarchy, and actually this is going to be the first time where we get to actually check that third level of the hierarchy, because in this case, the population, we don't know if it's normal or not, so we can't go off of level 1. On level 2, this sample of 8 is not enough to satisfy the central limit theorem, so we have to go to level 3. We have to graph our sample data. So this requires you to go back and think a little bit from Chapter 1, how do we graph sample data? Earlier, we had talked about this just briefly. The best way to graph this that I'm going to tell you is the easiest way to see this is to do a box plot, do a modified box plot, because it shows outliers and it shows skewness very quickly and very easily. So I'm going to pause the video here. I want you to go graph that sample data of 8, put your data into list 1 and make a box plot. If you don't know how to do that, you better review, talk to your neighbors, figure that out. So pausing the video, allowing you to go graph that sample data real quick. All right. So you have this graph on your calculator. It should look something like this when you graphed your box plot. Okay, so again, what are we looking for? Are there any outliers? Well, because this was a modified box plot, it didn't show any of them, so there are no outliers. Is there any strong skewness? Okay, so again, when we're kind of looking at the strong skewness, we're evaluating the median. Is this median fairly close to the center of this distribution? There is a slight skewness to the left. This median is slightly more to the right than it is to the left, but this thing, the median here, still shows fairly close to the center. It is not a strong skewness. So because this sample data did not show any outliers, did not show any strong skewness, we're going to say that it is approximately normal, and we can continue on. All right, and finishing up here with letter C. So we have a random sample of 25 bags of potato chips from the thousands of bags filled an hour. Of the bags selected, 3 had too much salt. So we know that we're looking at the proportion that had too much salt. So we're trying to figure out what percentage had too much salt. So this is a proportions problem. Conditions here, random. And it does say that they were taking a random sample. Condition 2, 10%. So is that 25 less than 10% of thousands of bags? Because it says from thousands of bags here. So 25 is indeed less than 10% of thousands, which would be hundreds. So the 10% condition is met. And finally, finally, normal. Large counts check. Okay, 10 successes and 10 failures. N times p hat has to be greater than or equal to 10. N times 1 minus p hat has to be greater than or equal to 10. Okay, well, this is where a lot of kids will get stumped. What's the p hat? What's my sample proportion? Well, you have to, again, read a little bit and think about it. My sample proportion, 3 of them had too much salt out of 25. So my sample proportion is 3 out of 25. So we could take 25 times 3 out of 25. But they already told you 3 of them were the successes. 3 had too much salt. Which means if there was 25, 22 were good. 3 successes, 22 failures in terms of too much salt. Is 3 greater than or equal to 10? No, so it fails condition 3. So this particular problem could not move on. But sometimes they're not going to give you the sample proportion. You're going to have to interpret or read and find it. So in this case, the sample proportion was 3 out of 25. Okay, so that's the conditions. Now, putting this all together, putting this together and actually doing the calculations with this. Real quickly, though, reviewing one more thing. Standard deviation, standard error. We talked about this yesterday with means. Real quickly with proportions. The standard deviation formula for sample proportions that we learned in Chapter 7. Square root of p times 1 minus p all over n. Once again, we don't know the actual proportion. That's what we're estimating. So when we change that to be the standard error for sample proportions, when we use the sample proportion as our estimate, we now call it the standard error. This is what we have to use when we're estimating a population proportion because we don't know p. Same thing happened with standard deviation for means. Formula from Chapter 7, standard deviation for sample means was a standard deviation of population over square root of n. We don't know this population standard deviation And so we have to change it to standard error, where we use the standard deviation from the sample over the square root of n. And when we do that, we now change the name to standard error. Okay, so putting this all together for the formula. One sample z interval for population proportions. Again, a one prop z interval. The formula for it is p hat plus or minus z star times the square root of p hat times 1 minus p hat all over n. One sample t interval for population means. This is a t interval. Is going to be the sample mean plus or minus t star times the standard deviation of the sample over square root of n. Don't overlook these names. They'll be really important for you to know the names of them as we move on when we start doing chapter 9, especially, and we do chapter 10, and we end up having like 10 different names of different tests that we're going to do. You will have to know the names of the tests, so don't overlook the names of the tests. Okay, so putting this all together now, to give you the way to do this, the easier way to do this, this is a 4-step process. State. There are 2 parts to the state for process. This is so that you can get everything there. This is kind of just a guideline to make sure you don't miss anything. State. We're going to give the parameter. And we're going to name the test. So this is a 2-step part for the state part of this. So we're going to say we're estimating the population proportion of students that eat breakfast every morning. And so then we're going to do a 1 prop z interval. Okay, so that would be the state part of it. The second part, the plan part of this. This is where you're going to check the conditions. Is it random? Was it gathered? Does it satisfy the 10% condition? My sample size is less than 10% of my population. And finally, does it follow a normal distribution? And again, this normal condition changes depending on whether we're doing means or proportions. So you have to go back to those conditions from above, and they change depending on proportions versus means. The do is your calculation. And the conclude is your interpretation. And again, this is that template that we learned in 8.1. We are blank % confident, so on and so forth. Follow this 4-step process. It will help you remember and not forget any of the key parts to this section. Let's put it all together. We're going to do 2 examples with this real quickly. Then you guys will have some time to work on your homework. Okay, so example 1 here. AP Stats wants to estimate the proportion of pennies. So we automatically know we're doing a proportion problem to see how many of them are more than 10 years old. So that's what we're estimating. So they gathered all the pennies in their pockets and purses. Overall, 57 of the 102 pennies had more than 10 years old. So step 1, state. P is the true proportion of all pennies over 10 years old. That's my parameter of interest. And to estimate this, I'm going to be doing a 1 prop z interval. Step 2 is to plan. This is where I'm going to check my conditions. Is this a random sample? Okay, so this one has a little bit of debate. We're checking for randomness. Is the pennies in their pockets and purses truly a random sample? Probably not. But did they really have a whole lot of control over the coins that they actually got? Maybe they did. Maybe they intentionally was at home and they were looking through their pennies or their coins and looking to find ones that were over 10 years old. They may have done that. So technically, this probably isn't random enough. So really, we probably should stop. However, because I want to go ahead and do this problem, we're going to say that yes, the pennies that was in their pockets and purses, they probably didn't have any control over it, so it's random enough. Probably not. That's one where I would be a little bit gray. Whether you said if you said on a test that it wasn't random enough and stopped, probably okay. Most of them will say they took a true random sample. However, when we're talking about coins, is it very easy to take a true random sample? Can we really number all the coins and gather them randomly very well? Yeah, probably not either. So that's one that's a little bit difficult in actual practice. Condition number 2 is the 10% condition. Overall, we gathered 102 pennies. So that is definitely less than 10% of all pennies in circulation. There are definitely more than 1,020 pennies. And 3, is it normal? Because this is a proportion problem up here, we're going to do NP has to be greater than 10, N times 1 minus P has to be greater than or equal to 10. And once again, because we don't know P, we're going to be using the sample proportion as an estimate for it. So in this case, they don't tell you what the sample proportion is, but they do tell you that 57 out of 102. So they give you your sample proportion that way. Another way of thinking about it is they had 57 successes. That is definitely more than 10. So if they had 57 successes, that means they had 45 failures. So that is also more than 10. So it is approximately normal. Okay, so there's my conditions. That's the plan part of this. The do part of this. Now we're going to put this all together and actually do the calculation. We're doing a 99% confidence interval. This is a Z interval because we're doing proportions. So the first thing I have to find is my critical value Z star. Inverse norm. 1.99 over 2, 0 and 1. This is my area. This is my mean. This is my standard deviation. So my Z star critical value for this one, 99% confidence interval, is going to be 2.56. So my sample proportion, 57 over 102, is 0.5588 or 0.559 plus or minus my Z star critical value, 2.56 times my standard error, which is going to be the square root of 0.559 times 0.441 all over 102. When I put all of that together, I get a confidence interval that 99% confidence interval, 2.56 for my critical value. I get a confidence interval that goes from 0.43 to 0.69. Okay, so then we turn on to our interpretation. Down here, we are 99% confident. The interval from 0.43 to 0.69 will capture the true proportion of pennies over 10 years old. All right, and finally, the last question here. Is it plausible that 60%, more than 60% of the pennies are over 10 years old? Well, if we look up here, 60% is in this interval, so yes. Because 60% is in the interval, it is a plausible value. Another type of question that you might see on something like this is it plausible that less than half of the pennies in circulation are over 10 years old? And because there are values that are less than 50%, then yes, it is also plausible that less than half of the pennies are over 50 years old. So be aware of a question like that. Sometimes you may have to do a little bit of interpretation with the question to see if that number is actually in the interval or not. Okay, so that's a proportions problem. Here's a means problem. Here's what I want you to do. I'm going to pause the video. I want you to go do this example on your own and then come back and check the video to see if you've done it correctly. So hopefully you took the time and actually went and did it and didn't just keep watching the video. If you did, here's what we should come up with. State, we're estimating the true mean weight of an Oreo, so we're going to be doing a t interval to measure or estimate that weight. Checking the conditions, it is a random sample. The central limit theorem covers us for normality. And there are more than 360 Oreos, so the 10% condition has been satisfied. Because it's a t interval, we have to do our inverse t. Forgot to put this on here, so this is my area, and this is my degrees of freedom. So we end up with a t star critical value of 2.03. Putting all that into our formula, we get an interval from 11.36 to 11.42. And interpreting it, we are 95% confident interval from 11.36 grams to 11.42 grams will capture the true mean weight of an Oreo. Now, the question that goes with that. On the packaging, it says that a serving size of 3 cookies weighs 34 grams. Does this interval that we just came up with up above give convincing evidence that the average of weight of an Oreo is less than advertised? Well, this was per 1 Oreo. This interval up here that we did was for 1 Oreo, and this is for 3 Oreos. So the first thing we need to do is we need to go back to 1 Oreo. The mean weight of 1 Oreo should be 34 divided by 3, or 11.33 grams. So, does this interval give convincing evidence that the average weight of an Oreo cookie is less than advertised? Well, this is what is advertised. And this is what we got from our sample. So no, the interval actually shows the average weight to be higher. The interval actually shows the average weight to be more than what was originally advertised. All right, so that's the process for constructing in confidence intervals. Go ahead and start working on the 8.2 and the 8.3 practice problems. If you don't have them, they are here on the desk at the front or on my desk here. I don't know where the sub has them or where they left them, but I left them on the corner of my desk there. So pick those 8.2 and 8.3 practice problems up. Be working on those. Monday, we will have a homework quiz over this, and we will finish up a couple more examples here on Monday, as well as doing this little bit down here at the end where we talk about picking the appropriate margin of error. So then we'll finish this up on Monday. Don't forget your test is Wednesday of next week.